I come from Ericsson Research. We are an 800 people large organization spread over 3 sites in Sweden, or 4 sites in Sweden, but we have some sites in Hungary, Germany, US, and so on. Totally, we have 26,000 R&Ds, and we're 100,000 people roughly. So what I'm going to talk about today is not sort of, I don't know what everybody's doing at the company, but I know what a few people are doing. And the purpose with this presentation is to tell what we're doing and drop a few use cases to illustrate how we use HPC and maybe also how we can use a larger facility in Sweden. So working in telecom is a 10-year cycle. Now it's 5G. So with 4G we got mobile broadband. It's basically you can watch Netflix on your cell phone. You can watch streaming video. Wherever you go, you have mobile connectivity. And with each generation, we typically try to do a 10-fold bandwidth increase, a higher throughput, lower latency, and so on. And with 5G that is being released right now, we have sort of enhanced mobile broadband, which will give you gigabit rates for your cell phone. But we have 2 more use cases, not just more Netflix to the people. We also have lower latency, so critical communication, hooking up your robots, getting close to millisecond latency round trip for controlling equipment in mines and factories and so on. And we also have another use case, which is massive communication, where you have lots of IoT devices. Imagine that you have devices that you buy on IKEA. You want the battery to last for 10 years. So then you have to be very, very careful when and how you communicate with that device. And all those different kinds of communication has different kinds of radios and protocols and so on. And it goes without saying that designing this is a handful. And we do everything going from chipsets, our own CPU, to servers, to boxes, to radios, antennas, whatnot. And then we operate those things for operators. And we will, of course, most of the people at Ericsson actually do software. And of course, I'm actually working on 6G right now. And 6G right now is we're trying to figure out what it's going to be. And the thing we're looking at is to have sort of the digital twin world, where we try to combine the digital world with the physical world. And of course, it's a lower latency, higher throughputs, tighter connectivity between the real world and the digital one. And of course, this is what we actually sell in physical devices, and we will hear more about those because designing those requires some careful HPC thinking. But on top of this, it's lots of software and management and operations. And we have one of our data centers. This is located in Rosersberg, outside Stockholm here. It's, if I remember correctly, it's 14 megawatt. But it's not only for HPC, it's also a testing facility where we test all the equipment that we build, all the radios and so on. But we have some HPC clusters in here running typically LSF or Slurm or similar. You know LSF? Is that some? Nobody knows. Load sharing facilities works and similar to Slurm. But then I have my own playground down in Lund. It's only half a megawatt something that we are running at Ericsson Research. And here we have roughly 1,000 servers and GPU clusters that corresponds to maybe 10 DGX boxes, roughly. And we're running OpenStack, and on top of OpenStack, we're building different kinds of large-scale simulation facilities, something that is running Slurm on top of OpenStack, and that's open to all the researchers at Ericsson Research. And I think most of the workloads that we are using at Ericsson is not traditional HPC. It's not, when I mean traditional, I mean tightly coupled MPI stuff. We don't see much of that. We see a lot, most of the jobs are very easy to parallelize. You do parameter searches over large couple, many jobs that you can run on a scale up very easily. So it's, if you want to go from 1 job to 1,000 jobs, it's just to spin up another virtual machine. And it typically can be maybe large user behavior, trying to figure out how users that use our equipment are moving around in a city. Wave propagation, chip design, for example, both building cryptos and building real CPUs. Thermal design, we'll hear about that from Achref in 5 minutes or so. Antenna design, and of course, machine learning for the last 5 years has been explosive. So we have something called Gaia Global AI Accelerator at Ericsson, which is employing us around 500 people right now, which are doing all kinds of machine learning. So we're getting machine learning into the physical layer of the network as well as the management layer of the network. So it's all over the place, and all kinds of machine learning, both supervised learning, unsupervised learning, reinforcement learning, whatnot. Lots of the things that we do is kind of sensitive, both in terms of the data, because the data is from the operators. So, and that can disguise both the structure of the network as well as the pattern of the users, which both is confidential. Secondly, the results, algorithm solutions are typically also very sensitive in terms of IPR. We do a simulation that might go into the standard, and before it goes into the standard, we would like to patent it. So it's we try to keep those under wraps. And also many of the things that we do is actually interactive. So you can sort of have some simulation model you would like to interact with. For example, having a reinforcement learning agent that interacts with a advanced simulation model. So it's not just batch processing. So to summarize this, I think that heterogeneous workloads. I think that this has been said several times today. I think maybe the picture is the best here. We quite often in our business, we try to, it starts with the research, we do design, people are trying things out in scikit-learn or, small scale. And then at some point, which is kind of unplanned, you would like to ramp things up. And this is very much a sort of a bottom-up thing. Somebody's picking up an interesting topic and, get that to work. And then at some point, you would like to scale it up. So it goes, having this, was it? Okay. Just maybe somebody getting bored. So I think this is something that we really like with working in a cloud fashion, where you can have small teams ordering the resources and scaling up the resources on demand. Super important for getting getting work done. So now I'm going to run through with 3 examples the way I think that is illustrating. This is something we did together with RISE. Here we have a computational fluid dynamics model where we're simulating sort of the airflow in a data center. So this is 2 racks or rows with racks. Here the cooling equipment, and now we try to figure out how can we control the cooling equipment and the workload in the data center such that we will reduce the power consumption. And if you have a data center in Lund, Skåne, where it costs 8 kronor per hour, you really would like to reduce the power. So it's not fun to get the bill nowadays. So here we interact with this model. So those models are running on A100s, and those reinforcement learnings are running on regular CPUs. And of course, doing this, finding out all the parameters you would like to figure for the reinforcement learning, the more of those you can run, the better. But of course, it's kind of easy to make this parallel because there's no shared data between the models and so on. Another example here is cryptography. So we're designing the ciphers for 5G and for 6G nowadays also, searching for the S box, which is substitution box for the streaming cipher, searching for the optimal circuit implementation, as well as for the weights for the linear feedback polynomials. Also things that are very well to sort of design space exploration. You try out lots and lots of variants, and in this case, performance versus scalability. It's having it in a cloud environment where you lose some performance due to virtualization versus the ease of use to just add more computational power. And I think ease of use and scalability is more important than optimal performance. And then we are working together with a company called NVIDIA I'll show you this small, cute video.
Ericsson is building a digital twin of a whole city to configure, operate, and continuously optimize their fleet of 5G antennas and radios. This is a really great story. Take a look.
There are 15 million 5G microcells and towers planned for global deployment in the next 5 years. Ericsson is using NVIDIA Omniverse to build digital twin environments to help determine how to place and configure each of their sites for the best coverage and network performance. In Omniverse, Ericsson builds city-scale models that are physically accurate down to the materials of the buildings, vegetation, and foliage. Then, wireless network components are added, including the precise location, height, and antenna pattern of each transmitter. Ericsson built a custom Omniverse extension, enabling them to integrate radio propagation data and leverage Omniverse's RTX accelerated ray tracing to quickly visualize and calculate the quality of the signal.
I think that's enough. So what we do here is we're using the RTX, the ray tracing that is used for gaming, but we're using that for wave propagation instead, trying to figure out how the waves are bouncing on the houses, and you go around corners, and then there would be another patterns of reaching from the base station down to the vehicle where you're actually receiving the signal. So this is just a good example of, again, workload that lends itself well to scalability. It's fairly easy to scale this up. We're using this Omniverse from NVIDIA fairly right off. So with that was some examples of, and we can have a deep dive from Achref. So
yeah, hello everyone. I'm Achref Rabhi, and I come from the thermal design team of Ericsson. So we are mainly more than 50 thermal designers around the world, and 40 of us are sitting here a few kilometers away in Kista. So I will be giving some examples about some simulations that we are doing for to cool our devices. And here I will be speaking about this device, which is called Remote Radio, and also about some antennas. So basically, we have it like this. We have many clients around all the world, let's say, and for each remote radio, you see, we have to figure out a cooling strategy. So it's not the same as we install the radio in Scandinavia, for example. It should not be the same strategy or cooling strategy if the radio is installed in Middle East, because mainly it's hotter there. And also, these remote radios can be installed in different configurations, in cabins, and close to antennas, very high. So that's why we have to run many different simulations and different studies in order to find or to figure out the optimal cooling strategy for that radio in order for it to stay cool, but also to be energy efficient, let's say. So yeah, in order to get the output that we are looking for always, better product and lower cost, we are having or we are building knowledge through some collaboration with universities, mainly through thesis works. But I think that for PhD, it's from more where you come from Ericsson Research. And also, we are using simulations. And for that, we are having some commercial softwares, or we are using some commercial softwares like ANSYS, Flowtherm, and StarCCM Plus from Siemens. And also, we are using open source tools like OpenFOAM. And these tools we are running in 3 different HPS solution, let's see, or HPC solution. First, we have Ericsson HPS desktop. Also, we have Windows cluster. And finally, we have an LSF cluster. And we are having these two both, the Windows cluster and the HPS desktop, which are based on Windows, because we have some main tools that we are working with. They work only on Windows. They cannot be implemented or working on Linux machines. Yeah. So the first case that I will be presenting here, it's the wind load. So basically, if you have an antenna installed 20 or 30 meters height, there is a strong resistance to the wind. So that's why we are running some simulations to figure out the best angle to put that antenna, let's say, to have the less resistance from wind. And after doing simulations, for sure, we have to do some experimental validation, but an experimental validation we can do only one. So that's why we have to run multiple cases in order to figure out the optimal configuration of installing this antenna. And this example of simulation, it was run on ANSYS Fluent using both Ericsson HPS desktop using 8 cores. And why we are using 8 cores on this one? Because it's really a big machine, but it's shared along all the world with our 50 colleagues from thermal designs and also from other subgroups in Ericsson. And one case, it takes 60 hours, but if we run it on our HPS cluster using 30 cores, for example, it scales up to 15 cores. The second case that I will be presenting is the most efficient cooling technology that you can find nowadays, which is two-phase cooling or phase change cooling. So the implementation of this, it has to be very, it has to be very well studied and optimized in order to get the best cooling performance and also in order to be in a safe margin, because usually this is closed systems and pressurized systems that can reach even up to 20 bars, and you don't want that to explode. And as of the examples, we are implementing or we are studying thermosiphons, as you can see here. And this is a two-phase simulation with phase change, the liquid change phase from, or the fluid change phase from the liquid to the vapor. And for example, one simple simulation, as you can see here, done with OpenFOAM. It's just a 2D case, not even 3D, using 252 CPUs. You need 168 hours in order to reach steady state. And this can be much more complicated, and it will take more time if we are, if we would like to simulate our real geometries, because as you can see here, this is the device that we would like to model, for example, and it contains more than 30 thermosiphon like this. The final case that I will be presenting today, it's the everyday work that we are doing. It's the air cooling for our devices, or the passive cooling of our devices. So basically, it's a conjugate heat transfer simulation. That means it takes into account all the heat transfer mechanisms that we know. It's a really very simple case. We have the tools to do it very fast, but the problem that for each case, we have to run multiple power budgets. Let's say for this case, for example, that you can see here, we have to run 30 or 40 different power budget. One case, it takes almost 2-3 hours, but if you would like to take into account all the power budget that you have, you need to run it for 40 or 60 hours. So what I can say here that in Ericsson, we are having some powerful HPC solutions, but we are always looking forward, because if we would like to take into account all the possible physics, the simulations became really computational hungry, and we don't know when we need to use an external, let's say, HPC solution that is better than the one that we have now. So yeah, to summarize, as my colleague Johan here presented, and as I showed you, we have a wide range of workloads that we have to take into account. And this makes, for example, in my case, the simulations, the number of simulations too high and the number of cases to be taken into account too much. That's why an HPC solution, it enables our work and it makes our work possible. We are focusing more on future artificial intelligence solutions, and it is increasing rapidly in our organization. The best solution to have in the future also, and also we are having it now, it's cloud style access to our resources. And more importantly, security is the main concern to have or to use some external solutions. So yeah, thank you very much.